Welcome to problem solving session 3. First I'll go over the RLC circuit example that we had in the lecture, just to brief up how we got the formula. Okay. Then I'll go through some examples for characteristic equation and how to go about solving them, then getting the impulse response, and convolution. Okay, so a few things on MATLAB and a few things I'll be writing down. Okay, so first let's go over the RLC example that we have in the lecture, just to relate how we generate the equation over there. So this is the sort of circuit we have. So XT is our voltage supply. One H is our inductor. 3 ohms is our resistor. Half F is our capacitor. Okay, and YT is current. Okay, so how do we get these equations? These are basic equations from your circuit theory. Okay, so we have resistance into current is voltage, 1 over the capacitance into integration of current is voltage, and inductance into integration of current is voltage. Okay, now coming back to the circuit, we will have L. Now we'll differentiate this twice, both of these equations, this once. So we will have L, second derivative with respect to time of current. L is the inductance, V is the voltage. Okay, and the same thing, just to get everything into dV by dt format, derivative of voltage. Okay, now in the circuit all of these currents will add up to the voltage XT, right? So the next step is just I'm going to denote the d by dt operator as capital D. So this is operator, it's not a variable. Even in your textbook, in your homework questions, capital D is an operator, it's not a variable, so be careful about that. Okay, so next is to write, now Y is representing my current, and X is representing my voltage. Okay, now putting back the values of R, L and C over here, we will have D square plus 3D plus 2 Y of t dx of t, and this is what you have in the lecture, this equation. Okay, and from this then you go on to the characteristic equation. Okay, make sense? Okay, now I'm going to do an example from the textbook first. So I'm going to do 2.2.4. Let me just write it down for you. So 2.2.4. What is given to us is a differential equation. Just be careful again that capital D is an operator, it's not a variable. Okay, and we are given that y0 is 2 and the dot on the top is the first derivative. Okay, makes sense? First derivative of y with respect to time. Okay, so now coming here to the characteristic equation, how do we write the characteristic equation? If you see, how? Yeah, so here, if you see this equation, the derivatives are added up in a linear fashion, okay? This only happens when your yt is an exponential, okay, because it has the same derivative, okay? So, your characteristic equation now becomes lambda square plus 9 is equals to 0, okay? So, what is this giving? This is giving us the 0 input response, okay? This term is 0 now, xt, okay? And we are just getting the response from the initial conditions. Okay, so the total response is the response from initial conditions plus the 0 state response. For 0 state, our initial conditions are 0. It's only the input available. Okay. Now, this is our characteristic equation. Next is just to find the roots for it. So now you'll have 3 cases for roots. You have real roots, you have real repeated roots, and then you have complex roots. Okay. Now in this case, what sort of roots will we have? Lambda square is minus 9. Correct, complex roots. So, and the complex roots are always conjugate of each other. Okay. Makes sense? So we'll have 3j and minus 3j. Okay. Now our final function is some constant. This is related to the in-class evaluation, the first in-class evaluation that you had. It was some constant times e raised to power some a plus bt, right? C2 e raised to power a plus a minus jbt, right? This is what you had in your first in-class evaluation. This was then written as some c e raised to power at cos bt plus theta, right? The same thing is used here. So now, since these are complex conjugates of each other, we will write it in this form. Okay? So our y now becomes c cos 3t plus theta. Okay? Here a is 0, so this becomes 1. Okay? C is there and cos, and b and 3 is from this term. Okay? Now next, what is the derivative of this y? Because you need to use the values that you're given to calculate c and theta. So once you have your roots, the next step is to use y, the initial conditions given to you, the y0s and the first derivative of y or second derivative of y, and then use that to calculate these constant values. Okay, so the derivative here is minus 3c sine 3t plus theta. Okay, now you equate this to these results. Okay, I'm not going to write that for you, you can solve it. So you will get c is equals to 2 and theta is equals to minus pi over 2. Okay, so your y t, oops, I'm so sorry. How
did you get the minus 3c sine?
You take the derivative of this y. So the derivative of cos is minus sine, right? Then you take the derivative of the inside term, the 3t plus theta. That's where you get the 3 from. Okay?
Okay, thank you.
Yeah. So next step is to just put in these values back into our equation, the main equation that we have here. Okay? So we'll have 2 sine 3t. Okay? Because it's 2 cos 3t minus pi by 2, and cos plus minus 90 degree becomes sine. Okay? So that's how you get your 0 input response. That's done. right? Next I'm going to do an example on how to get the impulse response, okay, from these equations, right? So let me pull that up. So in the question, this is 2.3.1, you're given d square plus 4d plus 3 yt is equals to d plus 5 xt. Okay. Now, first step is to get your roots from your characteristic equation, right? So again, your characteristic equation is lambda square plus 4 lambda plus 3 is equals to 0. So that's your characteristic equation. Oh God. I should have started this on a new page. Anyways, when you solve this, your first lambda will be e raised to power minus t. So this becomes lambda plus 1 lambda plus 3 is equals to 0. Okay? Putting this in, e raised to power minus t and e raised to power minus 3t. Okay? Makes sense? Why? Because our general formula says that lambda or y, oh sorry, this is not lambda, this is y. Let's say lambda 1 and lambda 2. Okay, so our general formula says it's this, c1 e raised to power lambda 1t plus c2 e raised to power lambda 2t. Okay, you just put in the values of lambda, right? Next we go to what? Now,
Can you show that page for a second?
oh sure. Is it clear at all? Okay, yeah. Yes. So your total y is sum of these two. Sorry? Yeah, with the constants in front. So these constants you calculate from your initial values that's given, that's y0 and y dash 0. These values that are given to you. Okay? So from these values you then calculate C1 and C2. What? Because it's 0 input response. Your input has to be 0. You set your input to 0. Okay? 0 state response is when your initial conditions are 0. So at one point you're putting 1 to 0. Okay? Your total response has two components. One is coming from the initial conditions part. One is coming from the input that you're applying. Right? So just to calculate it as a sum, you put one, set 1 to 0 and calculate the other. And that's how you go about it. Okay? Right. So in such questions, y0 and y dash 0 is not given to you. Okay? So in the textbook it is specified that for different degrees of equations, so here if you look at this, what is the degree of this equation? Correct, 2. So for different degrees of equations, these two take different values, okay, and they're given in the textbook, so you can refer to those, right? So for n is equals to 2, your y0 is 0 and your y dash 0, the first derivative of y, so this dot is there, is 1, okay?
For n equals 2 or n equals 0?
Oh, I'm so sorry, 2, okay? Right? So this is how, so now you have y is equals to c1 e raised to power minus t plus c2 e raised to power minus 3t, right? You have these values, you can calculate c1 and c2. So now 0 will be c1 e raised to power minus t plus c2 e raised to power minus 3t, right? And 1 will be is equals to minus C1 minus 3C2. And then you put t equal to 0 in these equations. Okay, so this will be 1 and this will be 1, right? These are at y at t equal to 0. Okay, so that's how you get your constants. So you have your characteristic equation, you have lambdas, you have your C1 and C2. Okay, now how do you go about getting your impulse response? So your impulse response is given as PD is nothing but this function. So hold on, this is not so whoa. Sorry. Okay, we're back. So this thing is called QD in the textbook, and this thing is called PD. Okay? So this is what I'm referring to over here. So PD is the one with your input, right? So how do you go about it? Then you have your YT and UT. So PD is D plus 5. YT, you know now, is e raised to power 2 e raised to power, one second, let me write down YT for you. YT you get to be half e raised to power minus t minus e raised to power minus 3t after calculating C1 and C2. Okay, so that's what you get, your YT. So you put in your YT over here, right, and then you go about D plus 5 YT UT. Now what will D do? So you have DYT plus 5YT. Okay, right? Now DYT will take the first derivative of your y function, right? So DYT will be the derivative of this, your half e raised to minus t minus e raised to minus 3t. Okay, and 5YT is just getting directly multiplied with this. When you add these two, your final answer will be this. Okay, right? So this is your HT. So you have your equation given, get your characteristic equation from there. You have a question? Yeah.
So you just have the U of T once you're done with the
Yeah.
impulse response?
Yeah, because it's causal.
Oh,
Okay. So U of T is there. U of T is just to show that your impulse response is causal. Okay. Okay. So to summarize the whole steps, you have your equation, you get your characteristic equation from there, you get your characteristic roots from there. Depending on the degree of your equation, you have your y0 and y dash 0 values. Okay. Using these, you get your constant values. Finally, you get your YT, that is your zero input response. Using that and the PD given in the equation, you get your HT. Okay, sounds good? Great. Now just to simplify the solutions over here, you can use MATLAB to get your roots as well. Okay, so let me just show it to you. Now, 1, 4, 3, the first equation is nothing but it's lambda square plus 4 lambda plus 3. Okay, which was the one we had in this example. Okay, so roots is the function that you can use to calculate your roots. They'll calculate in any case if it's complex, real, repeated. Okay, so now let's just run this thing. Okay, so we have -3 and -1. That's what you got in our first case. Okay, this is the case where we have repeated roots, and then another case where we have complex roots. So you just need to put in the coefficients of your equation. Okay, display is a command which displays the results in the command window. Okay, it's like printf you have in C, right? Num to str is just converting your number to a string, okay, for display purposes, because you have roots and then you have your number, everything all together. So it's converting your numericals to strings. Okay, so you can have str to num conversion also. Okay, there are a lot of conversions that you can do in MATLAB. It's like typecasting you have in C. Okay, next thing, this is again related to the example that we did, but it's sort of a different equation. So this is the differential equation that you have. Okay, now these, based on the second degree of this equation, degree is 2, your initial conditions will be 0 and 1, right? Now dsolve will solve a differential equation for you, okay, and it will give yn. Now your final impulse response is PD multiplied with yt, right? So that's why we have a diff function over here. Diff is taking a difference, it's taking the derivative of it. Okay, so that's how you get your ht, and it's displayed over here. Make sense? So everything that we've done by hand right now, you can do the same things in MATLAB. Okay, just to simplify stuff. And if you're using MATLAB for your homework, just include the code as well. So dsolve solves a differential equation, and diff takes the derivative of the function that you have. Okay, so from dsolve you'll get some function for yn, and then diff will take its derivative. Okay, okay, now coming to convolution. So there was a demo code shared with you guys, so let's just try and run that demo code. Okay. I believe this was the one. Yeah. So this demo code has 3 examples. So if you want to run this example, just remove the percentage sign. Percentage sign is for commenting a particular command that you have. Okay. So right now I'm running example 3, and then it's just performing my integration. So my integration, the delta term, it has to be kept very small, so you're approximating integration with summations and multiplications over here. Okay, right, and just go through the code, and if you have any doubts, let me know. Most of these commands, I think all of these commands we've covered, so you should not have any doubts. Okay, so let's just run it. So you take your h of x of t. In this case, you can take either h of t or x of t and flip it, and then shift it across the other function. Okay, it gives you the same result. Okay, so you just take one function, flip it, and then run it across the other function, and continue your multiplication and additions. Right, so this is just one demo. There is another demo that we have. Let me show it to you in discrete terms. It's very intuitive, and I'll share these links for these demos in these files with you. Okay, so let's set our x of n. So x of n is discrete over here, so it is present only at particular instances of time. It's not continuous. Okay, makes sense? Okay, so this, we've set it for length 10, amplitude is 1, so let's just set it. H of t, let's just decrease the size, let's keep it 4. Okay, now you can either flip x of n or h of n. Okay, either of them. it's not an issue which one do you flip, right? So let's start this thing. 1 second. Okay, so with every t, you're doing a time shift, right? So if your t is positive, it will shift to right. If your t is negative, it will shift to left. So in this sense, there's no point of shifting to left, right? It will be 0. Okay? Makes sense? If you're shifting your h to left, you're multiplying it with zeros. So your output is 0 in this case. Okay? Now, shifting it right, you'll get some overlap. Right? So your first overlap. So it's one pulse of h of t minus tau overlapping with your x of tau. Okay? And tau and t are just variables over here. Just don't get confused between them. Right? So tau is your integration variable and t is providing you the shift. T is helping you making the h function, impulse function, move across x of t. Okay? So as you move, your overlap is increasing. Okay, it's increasing. Now, at this point of instance, 4 pulses of your h of t minus tau and x of tau are completely overlapped, right? And now it remains constant. It's just 1 getting multiplied by 1 continuously. Okay, so it stays constant, and then your overlap starts to decrease, and then it's going to 0. Okay, makes sense? So this is basically convolution that you have. There's another demo that is there for continuous. So I'll show that as well. Oh no, I'm in the wrong folder. Okay. So this is the same thing. If you take this at discrete instance of time, it becomes a discrete signal, right? And over here it's at every instance of time, so it's continuous. Okay, so this is our x of t. Let's do h of t as this, right? Now, moving this thing to left gives us no output, right? So if your shift is negative, there's no overlap. As soon as you have overlap, your area increases and then it decreases again, right? So it's the same thing in continuous. Okay? Right, so how to actually know when the overlap is, because when you're answering a question, you can't use such a demo to answer your questions, right? So let's do it by hand for our example. Okay, so it's again a convolution of rectangular pulses. Okay, so let my x of t be a pulse of 1 duration and amplitude is 1. Okay, and let h of t be a pulse again, but it has the duration 3 and amplitude is 1. Okay, so now the first step is to flip, right? And you'll flip about your y-axis. So you can flip either x of t or h of t. Okay, right now I'm going to flip h of t in this example. Okay, so if you flip h of t, so you flip it, what will you get? Where will the pulse be? What is the starting point of the pulse and where will the pulse end? It's just time reversal. Okay, it starts at -3 and it ends at 0. Okay, so this is h of minus t now, right? Now next step is to shift this pulse across x of t. Okay, so shift h of, and now I'm going to start using tau as our integration variable. So shift h of minus tau across x of tau with each shift being t. Okay, and as you shift, keep multiplying and adding. Okay, right? Now let's see what values of t, the amount of shift that we want. So what will happen when t is negative? Where will this pulse go? Left or right? Left. So it will be a time advance, right? So what will we have is, this is our x of tau, and our h of t minus tau will be somewhere over here. Okay? Yeah.
How come when we graph and we do x of t minus some number, it moves it to the right, but when we do this, minus it to the left?
No, so t is positive in there. So when x, it's xt minus 3, for example, right? So now it will be centered at 3. When it's xt minus minus 3, so it will be centered at minus 3 now. So your negative sign remains the same. Here your shift, this 3 value is changing.
Oh, okay.
Okay?
Oh, I see, yeah.
Yeah. Right? So here the t value is negative. That's why it's coming to the left. Okay? So if you keep shifting it to the left, will there be any overlap? No, right? So no overlap. So from here we know that whenever t is less than 0, or y, which is the convolution of x of t with h of t, is equals to 0. Right? We can make that claim. Correct? Okay. Now next, when else will this be 0 again? When will y be 0 again? When?
When it's on the other side of the...
Correct. So when it will be like this, right? So this is your x of tau, this is t minus 3, this is t, this is 0, this is 1, right? So this happens when t minus 3 is greater than 1, that is t is greater than 4, right? This thing is more than this. Your left edge of h of t minus tau is to the right of your x of tau. Okay? So there's no overlap. So this is another condition when y is equals to 0, right? And if you keep increasing t above 4, it will keep going on to the right and it will be 0 always. Okay? Now, next thing comes, that is when it is between these values, right? So, okay. Now, when will we have complete overlap? This is an example of complete overlap. Okay. So now our t is here and t minus 3 is here. Okay. So t is greater than 1 and t minus 3 is less than 0. Combine these two conditions and t will be between 1 and 3. Make sense? Right? Any questions? This we are checking when it's completely over it, over the other function. Okay? Now, we have following. So, in this case, what will y be? when there's complete overlap between the two? Both of their amplitudes is 1. Correct, it's 1. Okay, so it'll be governed by this thing. This is your area. So your width is 1, your height is 1, your area is 1. Okay? Now, we have this condition that for t less than 0 it's 0, for t greater than 4 it's 0, for t between 1 and 3 it's 1. Now, our conditions that are left is when t is between 0 and 1, and when t is between 3 and 4. Oh, I'm so sorry. Right? These are the two time areas left for us. Everything else is covered. Okay? So for this condition, what will this condition look like? So this is your x of tau, the shaded region, and your h of t is here. So t lies in this region. Correct? Right? And this is your area of overlap. Right? So whenever t is between 0 and 1, what is the value of y? Width into height. Area under the curve. It's t. Your width is t, your height is 1. Okay? So as you start moving from left to right, your t will start increasing and your overlap is also increasing unless and until it becomes 1. Right? Make sense? Okay. Now when t is between 3 and 4, that means your t minus 3 is between 0 and 1. Right? So this is your x of tau, the shaded one. T minus 3 is between 0 and 1, and t is over here to the right. Now, what does the value of y? What is the value of y? It's this area. What is the width? Correct. So 1 minus t minus 3. That is 4 minus t. Okay?
Can you explain that?
Sure. So your width is this much. This is 1, this distance, and the smaller distance is t minus 3.
Okay.
So you're taking the difference between the two distances. Okay? So now you have the whole time range covered. Okay? So let's plot y, whatever y we have. So y is against t. Okay? So y of t, for t less than 0, we got y to be 0. Correct? So it's 0 here, t less than 0, and 3 and 4. So between 1 and 3, we had got y to be 1. So it's a constant. Y is 1 here. Between 0 and 1, we had got it to be t, right? So it will be with the slope of 1. And between 3 and 4, it was 4 minus t, okay? And then it goes to 0 again, okay? So whenever you're convolving two rectangular pulses, you get this similar shape. The size would change because of the width of the rectangular pulses that you use, but the shape would be similar. Now, just a question. If these two rectangular pulses were of the same size, what sort of a shape would we get here?
Maybe like a triangle, right?
Yeah. That'll be like a triangle, correct. Okay, because it's only at one instance of time that they're completely overlapped. Right? So, when rectangular pulses are of same width. Okay? Make sense? Okay. Now, let's just see if we can do another example. So 2, 4, 13, if you see, okay, it's of similar sort. So just go and practice 2, 4, 13, okay, and just see if you can get the same answer, right? It has different values for the widths, right? But your method should be the same, and you should get the right answer, okay, with this method. Right, next thing that I wanted to go over was, let's say you're given two systems, that you have H1T and H2T. And what is H1T and H2T? These are the impulse responses of your systems, okay? So H1T is impulse response of system 1, and H2T is impulse response of system 2, okay, right? Now these two systems can be connected in parallel, so this is your input and you have sort of an adder over here, okay, so your input is xt and your output is yt, so this is parallel, or it can be in series. Okay, one followed by the other, right? So what is the sort of output will we have? So yt will be nothing but h1t convolved with x of t plus h2t convolved with x of t, right? And in series case, you will have h1t convolved with x of t, this whole thing then convolved with h2t, okay? Because this whole thing is then as an input to h2t, right? Make sense? Any questions? No? Yeah. No, so convolution has the associative property.
Right, so
It doesn't matter, right? Okay. So this will be same as if you do x of t convolved with h1t convolved with h2t. It will be the same. Okay. Makes sense? Now I just want to go over next is stability, just to be clear about some terms. So stability. You have your external stability and you have internal stability, right? External stability is your BIBO stability, or bounded input, bounded output.
Could you say that?
Oh yeah.
Thank you.
Okay, that's your external stability. And internal stability comes from your characteristic roots. These characteristics roots are characteristic of your system. They describe your system. Okay, that's why it's called internal stability. Okay, so one golden rule to remember is, if system is internally stable, then it is BIBO stable, but the converse is not true. Okay, is not true always. Okay, right? So if you think of an oscillator like a cosine or a sine, That is BIBO stable, right? You give a bounded input, your output will be bounded between -1 and 1, right? But is it internally stable? No, because its characteristic roots lie on the imaginary axis. Okay? So let me define what internal stability means and how do you say that a system is internally stable or not. So from your characteristic equation, you get your characteristic roots. So I'm just going to use 2 roots in this example. You can have more than 2. So say lambda1 and lambda2 are your 2 roots. Okay? Now these 2 roots so if you plot these in the complex plane, okay, these necessarily don't have to be complex to be plotted in the complex plane. You can plot your real numbers also in the complex plane, right? So you have imaginary axis, you have your real axis, okay? So if these 2 roots are negative, okay, so you have an e raised to power minus lambda1 t term. No, e raised to power lambda1 term, lambda1 t term, okay? If this is negative, then this whole term goes to 0 as t goes to infinity. Okay? One. Yeah. Sorry. So you have e raised to power lambda1 t. So when lambda1 is negative, so let's say it's e raised to power minus 2t, for example. Okay? This you can write as 1 over e raised to power 2t. Okay? So as t goes to infinity, your e raised to power 2t goes to infinity. It's an exponential function, it will increase exponentially. Okay? So 1 over e raised to power 2t will now go to 0. Okay? So for your system to be internally stable, the real part of your characteristic roots should be negative. Okay? So if the real part is negative, this is the area where your characteristic roots should lie in, which is called the left hand plane, or LHP. Okay, so left hand plane, right? Your roots should lie in this plane, not on the imaginary axis also. Okay? Not on the imaginary axis.
So the third quadrant?
Third and fourth quadrant.
Okay.
Yeah. The imaginary axis is not included in your stable area, if you might say. Okay? Now, there are 3 things that you can say about your system when you have your roots. So if real part is negative of all the roots, okay, then your system is absolutely, it's stable, okay? It's internally stable. And if it's internally stable, you can for sure say that it's BIBO stable. Okay? Bounded input, bounded output stable. If any one of your roots lie on the imaginary axis, so if any one root lies on the imaginary axis, your system is called marginally stable. So for a cosine or a sine, it's an oscillator, right? It keeps oscillating. It's not going unbounded, it's not going to infinity, it's not completely unstable. It's stable in some sense, but it's not completely stable also. Okay? So that's why it's called marginally stable, right? If your roots lie on right hand plane then it's unstable for sure. Okay? Makes sense? Any questions? Now let's just see if we have any examples.
Is it possible to have it where you get a root on the right-hand plane and the left-hand plane?
It is possible, and it will be unstable because of that one root. Because something is there on the right hand plane.
So the right-hand plane would override the left-hand.
Yeah.
Okay.
It's very easy for your system to become unstable. Okay?
And then on the second one, where you said it lies on the imaginary axis,
Right.
do you mean like if it doesn't have any, if it's like minus 3j, it'd be marginally unstable. But if it was like 2 minus 3j, it's not on the axis, but it still like has an imaginary part.
It's unstable. So right hand plane includes positive real part and either positive or negative imaginary part, or zero imaginary. It can be either. So this is your right hand plane. So your root can be here, where your real part is positive and your imaginary part is positive. Your root can be here, or your root can be here. All these three are unstable.
And then if there's like a dot that was like minus 2 minus j, that would be stable, right?
Yes.
Okay.
Okay?
Is the natural form of the root to the quantity, is that always zeros and negatives in there? Like that's kind of random.
No, no, there's no negative here.
Oh, so usually it's just e to the.
Yeah. Okay? Makes sense? Right. Let's see. I'm just going to look over for some examples, if I find them. 2, 4, 11. Okay, I think that's about it. I'll be here for my office hours. Okay? So that's about it. Thanks, Daniel.